In the previous video, we finally completed SN1 and SN2 reactions. In this one, we are going to be talking about elimination reactions. So essentially, we finished substitution reactions, and in this one, we're going to be talking about elimination reactions for haloalkanes and haloarenes, but we're obviously going to be focusing on haloalkanes. Now, in first of all, the word elimination, obviously, you know there are four different types of reactions. I'm sure you learned addition, substitution, elimination, and I forgot the fourth one. Comment below. So, the elimination reaction involves the removal of the hydrogen and the halogen atom, and this leads to the dehydrohalogenation reaction. So, essentially, what's happening? Dehydrohalogenation is happening here. Okay, so first of all, the hydrogen that gets kicked out from this molecule is going to be something called the beta hydrogen. So when you have these two carbons, this carbon is considered to be an alpha carbon and this is the beta carbon. This is the alpha carbon because it is attached to the functional group. This is the beta carbon because it is attached to the alpha carbon, and the hydrogen atoms attached to the beta carbon are called as beta hydrogen atoms, and these are obviously going to be alpha hydrogen atoms. So when you have a base that comes in, so we're going to call it B minus, it's going to come and try and grab this H as a H plus, and then this bond is going to just shift over here, and then this is going to get kicked out. So you're going to have the elimination of the H and the Br because of the attack of the base, and this leads to the formation of an alkene. What is it forming? An alkene. Okay, so essentially this is what's happening in elimination, and we used alcoholic KOH and we heated it. Okay, now this led to an elimination reaction. This is all fine because this case it has only one beta hydrogen atom, or like there are three different beta hydrogen atoms, but it's only on one side, right? There is no other carbon atom attached to this carbon, so it's easy. But when you have multiple carbon atoms attached, so here what's happening is, let's take this bromopentane. Okay, you have CH3, CH2, CH2, then you have CHBr, and then you have CH3, right? So this is our 2-bromopentane. Now, in this case, this is going to be your alpha carbon because it has this bromine atom attached to it. So this is going to be an alpha hydrogen. So the beta carbon, you have this one and this one. There are two options, right? And so that means this, and these hydrogen atoms are all going to be beta hydrogens. So there is a rule called Saytzeff's rule. According to this rule, and this was given by Alexander Saytzeff in the year 1875, what he says is, in dehydrohalogenation reactions, the preferred product is that alkene which has greater number of alkyl groups attached to the doubly bonded carbon atoms. What that guy is saying essentially is that we prefer, in the end, we want an alkene which has more number of alkyl groups attached to it. Okay, so essentially what it means is that, let's say you have this, if the product was CH and then CH3, the product is more preferred. Okay, so we want a more substituted alkene. Okay, now let's write down the products for this particular reaction. So it could be the base coming in and then attacking this hydrogen, this shifting, okay, and then this getting kicked out, right? So that product is going to be CH3, CH2, then you'll have the CH, double bond, CH, and you'll have a CH3. This is product number 1. Product number 2 will be the same, or almost the same, not the same, obviously. And then this bromine atom is going to get kicked out. So you'll have CH3, CH2, CH2, CH, double bond, CH2. So this is the second product. Pause the video right here and try and name this using the nomenclatures. You have pent-1-ene and pent-2-ene. Okay, so between this and this double bond has a carbon which is attached to one alkyl group. This carbon is attached to another alkyl group. Okay, this is an ethyl, this is a methyl group. On the other hand, this double bond, you have this carbon, it's attached to two hydrogen atoms, and this one is attached to a propyl group, right? So essentially, this is a less substituted alkene, and this is the more substituted alkene. And according to Saytzeff's rule, in dehydrohalogenation, we prefer the more substituted alkene. So this will be our major product. Okay, this is going to be the major product. This will be the minor product. Remember, the reason I said major is because the percentage of this is 81% and this is 19%. So what this means is the base can attack from either side, okay, and it can form either of these products, but it prefers to form this one over the other. That does not mean we don't get any of these molecules at all. We will have some amount of the one pentene formed, but we prefer to have the major product, which is the 2-pentene. Okay, that makes sense. I hope it does. So in the beginning of this video, we said KOH is getting added. So then in the beginning of this chapter, you probably learned the fact that when you have a sodium hydroxide or potassium hydroxide as the nucleophile, it undergoes substitution reaction. You can be like, wait, didn't you just say that we can use that for elimination? Well, fun fact, the al haloalkanes tend to undergo either elimination or substitution based on how they feel. This is so essentially what happens is it's based on a few factors. Okay, now first of all, let's start with the main thing. The fact that we use the exact same potassium hydroxide in both cases, and here I said, oh, it'll undergo elimination, but here it's so clearly mentioned that it undergoes substitution reaction. So here, remember, we've used alcoholic KOH. Alcoholic KOH tends to make sure that our molecule undergoes an elimination reaction. What does it undergo? Elimination. Whereas if you have the KOH in water, then it undergoes the substitution reaction. This is because water tends to like to make sure that the formation of nucleophile takes place, and that in turn leads to the substitution reaction taking place. So basically, the ability of the haloalkanes to undergo elimination or substitution depends on the nucleophile itself or the haloalkane. Okay, so when you talk about nucleophiles, usually very strong, bulky nucleophile will prefers to act like a base. So what it does is it abstracts the proton and then it leads to the formation of an alkene. Whereas if it's a smaller nucleophile, it'll act as a substitution. It helps in substitution reaction. So bulky nucleophile prefers to act like a base, whereas a smaller nucleophile will help in the substitution reaction, gives out its nucleophile, and then it undergoes a substitution reaction. Also, a primary alkyl halide will prefer an SN2 reaction. So primary alkyl halide would probably prefer, if given a choice, it will want to undergo substitution reaction. A secondary alkyl halide, depending on it can undergo both. It can undergo substitution as well as it can undergo elimination. And this is entirely dependent on the size of the nucleophile. This is because it needs to be able to attack. Remember when we talked about the nucleophilic substitution reactions, we talked about how the steric factors affect the ability of it to undergo SN1 and SN2. And that obviously has a huge role to play in if it wants to undergo substitution or elimination reaction. Similarly, tertiary alkyl halide would prefer either SN1, right? SN1, or it can also do the elimination reaction. And this is entirely dependent on if the carbocation is stable or not. So stability or of the carbocation will in turn determine if it is wanting to undergo an SN1 process or the elimination process. So with that, we're done with elimination reactions. Remember, elimination reactions is basically dehydrohalogenation for alkyl halides. So it leads to the loss of H and Br, and the hydrogen gets kicked out from the beta carbon. The beta carbon is the carbon. Sorry, let's start with the alpha. Alpha carbon has the functional group. Beta carbon is attached to the alpha carbon. Hydrogen atoms that are attached to the beta carbon are going to be beta hydrogens. So essentially what you need to remember is that dehydrohalogenation is taking place, and that leads to the formation of an alkene. Now an alkene, if it is a more substituted alkene, that is what is more preferred according to Saytzeff's rule. So that's another important key takeaway from this video. And the third one is there is a possibility for these haloalkanes to either undergo elimination or substitution. This is entirely dependent on two factors. One is the strength and the size of the nucleophile, and the second is going to be the strength or the size of or the nature of the haloalkane itself. With that, we're done with this particular concept. In the next video, we will be talking about, let me see, oh, reaction with metals. Oh my god, we have Grignard's reagent. Grignard's reagent is really cool, and we'll talk about that in the next video.